to cover the weeks, it would be week 1 to 8. So it's covering to just recapping all week 1 to 8, which is done for quiz 1 and quiz 2. So, but the rest two revision session would be for week 9, 10, and 11, 12. So the next session would be for 9, 10, and the next last revisions would be for 11 and 12. So this is how the plan. So as you know, we this is covering week 1 to 8. So there is lots of topic. Okay, we'll just, so what we can do, I didn't took the question. I will create the question in front of you. We'll discuss the topic wise. I have listed all topics which is in week 1 to 8, and slowly we'll touch them. I means we'll quickly touch them, discuss a bit about, and then move to the next head topic. So there are if you see it, there would be I think 9 to 10 topics are there within, and even I have just noted those all for as an important topic. So let me share my screen, then think. See, so these are the topics we have, which is under week 1 to 8. So like vector space even first, and then basis, change of basis, linear transformation, matrix representation, range null spaces, okay, four fundamental spaces, determinants are there, and then most, which is these topics are even, I will say, important even for week 9, 10, 11, 12 also to understand, because even for week 10 and 11, or sorry, 9, 10, 11, 12 are based on this eigenvalues, eigenvector, and knowing to be the diagonalizability, algebraic geometricity, geometric multiplicity, and also there is a, we have seen circular matrix already there, but it is also available between week 1 to 8. Anyhow, once we have the diagonal matrix, then we can easily get the power of matrix. So these are some important topic where I will say the emphasis on, in place of discussing, I means I will discuss all surely, but I will give the emphasis on this linear transformation, matrix representation. Okay, and even we can say the four fundamental spaces are usually important, and these are eigenvectors, eigenvalues, AMG. At least these topics are used to very much clear with this and have a practice. Okay, these topics. So if you say the questions may come from these topics, like change the color, this linear transformation, and this matrix representation, surely range null. Even we can, if you want, we can include the inverse of linear transformation or matrix. Okay. Yeah, it is surely this eigenvalue, diagonalizability, and at least the power. Circle end is anyhow important. It is important to be here week 1 to 8 also, and it is already in 11, 12. I think in 12. So anyhow, this is the part of week 12. So it is circulant is, and very much, you can say, very very important. And we have discussed, we have written down question on circular matrix. We have discussed this in great detail also when I took the session on last session for week 12. Okay, so we'll quickly discuss these topics. We'll spend more time on these topics which I am saying important. In inverse is also important. However, you are finding the inverse, it doesn't matter. Okay, either you are finding with um, doing the, no, by this method. This side is writing matrix and this side the inverse, sorry, identity, and then changing to identity. This one as the second part become inverse, or it could be of you doing on finding the minor cofactor using that adjoint, finding the adjoint, and then inverse. Okay, so it doesn't matter however you are finding, but most thing is that you have to find the inverse at least. So let's start these topics. Let's look at one by one, one by one. So vector spaces, I will say we are going to look at only the vector spaces R2, R3, R4, or maybe till R5 or maybe R5. It will not go any question. I don't think it will be go beyond of R5. This much is enough. Or if it is beyond R5, then talking about Rn. Rn could be a, if it is the a question would be asked for Rn means it is a surely some theorem, some statement would be there. So more or even vector spaces of C2, C3. That's all. So these are the vector spaces. Okay, uh, which is important. When these are the vector spaces we have. So first of all, is this fine to discuss by this way to all of you, or do we want some any other method to discuss it? Have any suggestions for me to proceed with the any different way? Anyone wants to say something? Any doubt? Wants to suggest something to go session with a different method which you want, all of you want? The mock is, yes, the pattern whatever you are able to see, that is exactly following the interim is actually following that pattern. Mock is, you can say, a template. Even not only the template, yeah, I will surely discuss that. Even the I will more emphasis on the questions. We'll discuss a bit concept and more emphasis on question. Okay. And yeah, I was talking about this question paper, no? So question paper is, I will suggest you, even if you're not going through uh, even you are not going through with these topics all, but you should to go at least whatever the topics or questions are there in mock. So, so mock have some questions, mock have questions with the different topics. So go through with those topics. This is important. Okay. Okay, this is important.
Excuse me, sir.
Yes.
So can you tell the high weightage topics, like from which
So
topic?
high weightage topic is yeah, that is what I am saying. No, we'll discuss one by one. So high weightage topic for week 1 to is just now I mentioned in the this uh, color, right? The different color. I have these topics already, but the high weightage topics are linear transformation, matrix representation, inverse of matrix or linear transformation. Yeah, surely this eigenvalue, eigenvector. These are the possibilities. Even if you see the question, some question would be from here. So mock is very much giving you idea that which topic even more important. If you're not going through with these topics, it will be not that much impact, but you should to go with the surely mock. Whatever the questions are there, whatever the topics, whatever the topics from where the questions came, you should to do, you should to go with that, clear with that, and practice the questions related to that. Okay. I will again suggest you go through with your graded assignment questions of whatever available in mock. Okay. Okay. So I try to solve that. You may get similar question as in the graded. So if you just practice your graded questions, even that would be also suffices to get good marks in it. Okay. I think this much idea is very like giving this much related to the question paper is I think enough. Okay, let's start now. So vector spaces, you know already what is these are. You are doing all everything from even scratch of this maths too. So vector spaces is not need to discuss. Yeah, basis is important. I'll just quickly discuss that basis. So basis is, as the name is there, basis. So basis is important in the case of, it will, if you have a vector space, no, as we have R2. So you have seen that some vectors of 1 0 and 0 1, these kind of vectors you have seen. So if you are saying any element of R2, which is written generally, in this fashion, any element, this could be written as of using these vectors, x time 1 0 plus y times 0 1. So operations or other things I'm not going to discuss in the vector space because you are
Uh,
doing from longer
these
time this. Yes.
are these are
Mhm.
canonical basis, sir?
Yes, this is a canonical basis. So I was going to tell you that this is a canonical basis of R2. So let me list out some canonical basis. So like this is canonical basis of R2. Canonical basis for R3 is generally, not generally, this is the only one. This is canonical basis of R3. R4 is just extending the term. Right? Already it is just increasing form. This is 0 0 0 and 1. So this is canonical basis of R4, and similarly you can extend for R5 and R6 or whatever. So see that how it is. If it is R2, then two elements are there as in the canonical basis. So what is a canonical basis? Canonical basis is of this form. There are, for one vector space for R2 even, for R2 there is another basis also, 1 1 and 1 0 even I can take. This is also a basis. Okay, but this is just a basis. Here of this very specific basis is called the canonical basis. This type of 1 0, and at one place it will be non-zero, at and the rest all entries should be zero, as here you can see for others, for R3, for R4. So these are the canonical bases. So except that there are, for any vector space, infinitely many bases we have generally. Like even you can take -1 and 1 and 1 and 1. Okay, this is also a basis of R, another basis of R. So there are lots of bases. Okay. Even so, for this case, you can write this is a vector of R2. You can represent like this. So similarly, you can even you can write this vector as in this fashion also. So now tell me that this is a change of basis. This is now the change of basis. I am going to discuss it. So this is why. So can you tell me what is going to be here the coordinates? What is going to be the coordinate on the basis of this one? All of you just do this problem very quickly. What is going to be, okay? So here is alpha and beta. Let me change with the 2 and 3.
Alpha
So
plus beta comma beta.
okay, so what is going to be here alpha and beta value?
5 and
5 and 3. No, no, I don't think. 5 and 3 in place of 5 and 2 and
Alpha equal to 3.
3. Sorry,
Alpha equal to 3.
alpha is equal to 3. Yes,
beta is equal to
alpha
And
minus
beta equal to -1.
-1. Yeah, this is what it is. So it could be quickly done that, this form a system of linear equation. So this is one use of system of linear equation. Here is alpha plus beta. This is written as alpha plus beta, and the next is just alpha. This is equal to 2 3, as we know. This is how the operations done on vectors. And now this is just need to compare it. So this is alpha plus beta is equal to 2 and alpha is equal to 3. So now I just need to solve this. This is a system of linear equation. You know it very times, like even from doing this You know the Gauss elimination method is changing to, there are so many method, elimination method or any other method. Following that, you can solve easily. So this will give this value, alpha is equal to 3 and beta is equal to -1. So see, this is previously this 2 3 is, it is whatever the vector this given, this vector is given with respect to canonical basis. So this is one use, this is what the canonical basis is. A vector is given which is okay, which is and it doesn't so it is not specified that on which basis it is given. So it is automated, or it is understood, or by default you can say it is given with respect to canonical basis. Okay, any vector is given, it means by default it is given to the with respect to canonical basis. But now we want to check it this vector with respect to another basis which is a different basis. So this is a change of basis is happening, means it's represent the same vector, but now the vector with respect to this basis is 3 and -1. The basis is here slightly different. So this is what it is, representing the same vector but slightly different. So this is generally called change of basis. There are so many methods. So there is a matrix method to represent that. Okay, I will discuss that slowly. I will write the formula also. Okay. So this is the change of basis, one thing. And yeah, there are some properties that we know now what is the basis. Basis is to represent a vector, means it's actually the all vector could be represented within that basis. So but when we can say any vector, let's say 1 and 0 and 1, when this will be a basis, when set of vectors will be a basis. So if you see, the definition of basis is needed that this vector should be independent. Now the term started coming independent. So what is independent? Independent means if you write the linear combination, now the word is now added, see, linear combination. Linear combination is generally this one. This is a linear combination of these vectors. If you take the linear combination of these vectors and equate it to 0, okay, and if you start solving, if we end up with alpha is equal to 0 and beta is equal to 0 also. So in this case, it is called these two vectors are independent. So this is a linear combination. I took the linear combination, I equated to 0. Okay, and if when I started solving this, I end up with the 0 solution. So in this case, these vectors called independent. If you are not getting 0 solution, non-zero solution you are getting, in that case, these two vectors are dependent. Okay. So this is what here the basis, and there is one word is span. I didn't mention that span word is there. Span is once we have these vectors. Okay, once we have these vectors, so I said no, the linear combination. I took the linear combination. This is a linear combination of these two vectors. Now I am taking a very general, means I am not specifying. Like let's say I am giving an example, beta 0 1. So this is I just took, I have these two vector. I wrote the span of this. Okay, which is this one, which is the set, which is this set. What it means, it is actually collecting the all possible linear combination. Okay? It is collecting the all possible linear combination of these two vectors. So by this way, you can substitute alpha is equal to c. Alpha and beta are any real number. You can give any value to. Let's say alpha I am giving 5, beta I am giving 2, and by that way you can generate a vector 5 1 1 plus 2 0 1. It will give a vector. I can even change alpha value to beta value, and then again I will get generate a vector. All will be within the set. So this span is a collection of all possible linear combination. Okay, so this is called span, this is called basis, and this is a linear combination, and the independent dependent thing are there. So these are the ideas. Are this is week 1 content is there. Someone wants to say something? I've unmuted yourself. Yes. Okay. Naman can mute. Very less student have joined. So these are some span basis. These terms are there, and there is a change of basis. So we just now discussed what is the meaning of change of basis means. The same vector you are looking with the different basis. Okay, and generally this process you can follow to find the change of basis. So this is called a change of basis with respect to the vector. We'll see the change of basis in case of linear transformation also. Okay. We'll see there is another change of basis term words are there with the linear transformation. So let's look at the linear transformation now. These are some very concise definitions of span basis, change of basis, canonical basis, linear combination, dependent, independent, and span. Okay. So there is now something from R2, even R2, Rn. I will be now mixing to any. I'm not specifying R2 to R, only just R2. I could take any R2 to R3 or R3 to R2. I'm saying a general linear transformation. Linear transformation is nothing but, as we have seen, these are the mapping. These are just a function. But you, whatever you used to do, that is a simple from R to R. But here, slightly different thing is there. It is from R2 to R3. So surely means coordinate wise, here is it contain more variable. R2 means it contain more variable. Okay, and nothing but there could be a relation, as here the relation is there. There will be a relation with the t coordinate. So this could be of this case, this kind of representation. So linear mapping it is called when the each term have degree 1 and there is no constant okay added in that. If you add c, so this is not a linear transformation. Okay, each coordinate have degree 1 and each term is have degree 1 only. Okay. Whatever the variables it have degree 1. So this is generally called, and also some definition is there that if you have a, let's say, a linear transformation, when a transformation is called linear transformation, when it will be follow these two definitions. It will be spread out with respect to addition of the vector, and the second is alpha time v is alpha time tv. Scaling the vector to and then taking the image is nothing but the taking the image and then scalar. So these are those two definitions. If a mapping is following, and it's called linear transformation. So we have all of you from maths background, at least in 12. So there from starting, even in 11, 12, you have seen the matrix. Matrix is nothing but an array with the arranged form. The numbers are written in the arranged form. Matrix are nothing but this is. But the thing is that there is a relation with the matrix and this linear transformation. That's why we started looking, even you can say which one is came first. If you compare the linear transformation came first or matrix. So I will say that matrix came first, then the linear transformation another thing, or maybe not. Uh, the first thing I will say the matrix came, then slowly the theory developed for linear transformation. Because once we started arranged form of arranged form of uh, started arranged form of this number, then slowly look at the related to the functions, you can say. So matrix and there is a one corresponding between these two. Okay, and if you have this, you can convert. You can think this matrix, this linear transformation in matrix format, that is called matrix representation. And generally we thought the matrix representation with respect to the canonical basis. maybe this could be given for any other basis also. So canonical basis of R2 is, we know, right, 1 0 and 0 1, and for R3 we know 1 0 0, 0 1 0 and 0 0 1. This is a canonical basis of R3. So if you try to find the matrix representation of this linear transformation, what is going to be? All of you try this. Can you try it? And can tell what is the matrix representation? Anyone can tell that what is the matrix representation here? Anyone is solving that problem? One, okay, 1 and 1, and here is 1 0 1. Okay, let's see that. So generally the process is
1 minus 1. 1.
1.
1
What?
1 1 0 and 1 minus 1 1.
Okay, 1 minus 1 and 1.
Yes, sir.
Okay. So no, but here
We have to write it column wise, na?
so that is what here it should be,
Yes. 1 1 1 1 0 and 1 minus 1 1. Yes, sir.
This is going to be
Yes, sir.
yes. So generally what is that here is the way it is finding that you will take the canonical basis, find the image. So here it is, the image is going to be 1 1 and 0, and write this 2 as a first column. So this is going to be, so this is going to be, the first column is 1 1 0. Okay. So how many numbers are there? This one, the order, these two define the order of matrix. So this one gave the number of rows, and this will give the number of columns. So this is going to be 3 cross 2 matrix, 3 rows and 2 columns. This will give the number of rows, and this will give the number of columns. So otherwise, if you're not able to recall that, you can just quickly in mind you can say that, okay, the image is similar to this one, and then you can take the second image. This is going to be the image of the second canonical basis. This is going to be 1 minus 1 and 1, and now you can write vertically to this one. So here, once you find the image, you have to write in vertical form. This is not in horizontally as we wrote or just you told. So they have to write a vertical here. Please remember it many times. We are doing from many times. Whenever we used to write a linear transformation, we generally write the matrix representation also. So simply. Okay, so we have this linear transformation where the matrix representation is this one. So very simple. Even if you have a matrix representation, let's say I'm 1 2 3, I'm writing, and 1 1 1 and 1 0 1 is I'm writing. Okay, let's say I have a linear transformation from R3 through R3. Okay, what is the expression now here? Anyone can tell? What is the expression if the matrix representation of it is this one? Anyone can tell what is the expression?
X plus y plus z equal to 0, 2x plus y plus equal to 0, 3x plus y plus z equal to 0.
This is the expression. Very simple, very simple. You just need to take whatever you are writing here, no, take here vertically, and now do the matrix multiplication. So this will give a column y. So this will be here x plus y plus z, 2x plus y plus 0z, 3x plus y plus z. By this way, you can easily get the expression of that. See, very simple. Whenever you have a matrix, you can convert or you can get the linear transformation of it. Or if you have a linear transformation, you can easily convert to the matrix representation. So this is one correspondence between the linear transformation and the matrix. So now there is an inverse. There is an inverse term of it. So there is a composition also. So composition, let's say I have a linear transformation from R2 to R3, okay, and another linear transformation G from R3 to R2. So this is we have. So there is a one composition, as you know, T compose G. Okay, I just let me make it is T compose S. Okay, T compose S. It means that as you usually do the composition T of S of X. And here this composition is whatever the expression is there, finding the expression in place of writing uh, x variable, y variable, you can think whatever the corresponding variable, you can easily find it. I mean to say, if you have this composition, if the matrix representation of T is A and this is a B, then matrix representation of this composition is nothing but A times B. The order of matrix is 3 cross 2, as just now the same, and here is our order is 2 cross 3, right? This will give the 2 cross 3. Now you can, the composition is so this is going to be decompose as is going to be from R2 to R2. No? So this is going to be 2 plus. I think I'm making mistake. Here is this is 3 rows, 2 column. So this is going to be 3 rows, 2 column, and here is 2 rows and 3 columns. If you multiply, here we'll get A is of 3 cross 2 and B is of 2 cross 3. So the outer will come there. So A, B is going to be of order 3 cross 3. Am I making mistake somewhere? Let's do one problem here. It will be very much clear. So let's say I have a T of X and Y, which is going to be the same T. I am taking this T, X plus Y and X minus Y and Y. So this is going to be X plus Y, X minus Y, and just Y. And S is going to be, let's say, X, Y, Z, which is X plus Y plus Z, and X minus Y minus Z. This is the two linear transformation we have. So we have calculated the matrix representation just now, which is 1 1 0 and 1 minus 1. 1 1. This is going to 1 minus 1 and 1. What is going to be for this one? Anyone can tell quickly? Matrix representation.
1 1 1 1 minus 1 1 minus 1.
1 1.
So row
1
is
1 1.
1 1 1 minus 1 minus 1
1 minus 1
minus 1.
Okay. 1 minus 1, and this is it. Yeah. This is also easy. You know how we are getting it. This is image of t of 1 0 0 will get here. So easily it will
Sir,
be 1. Uh,
we can
yes,
see the
yes.
coefficient and write the matrix now.
Yes, using that is what it is. Writing this is as a this one, and similarly. So these are the coefficients here. Yeah. So you have practiced, so that's why you know easily that this is going to be the coefficients here. Whatever the coefficients we have, we write the vertically this one. This coefficients and this coefficient, right? We wrote the vertically like this. So this is what it is generally. If you do lots of practice, you can easily get it. Now T composes. T
So
composes.
in exam, we need to write the image and write the coefficient, or how?
So it's better to, if it is a subject you are writing, so write even this by this way, that would be good, no? Otherwise, you know it, it doesn't matter. But if you are making mistake directly here in this, so you lose marks.
Okay, okay, sir.
So this is the so T of S, which is just doing to be here. This is A, this is B. So here is A cross B. So this is 3 cross 2, and this is 2 cross 3. So it will be matrix of 1 by 1 we will multiply 3 columns, you will get 3 rows, you will get a 3 cross 3 matrix. Now see the order here. The order of a matrix is 3 cross 2, and this is 2 rows and 3 columns. So this is what it is. Here we just know to know. Yeah, it is what it is. We got 3 cross 3 order of matrix will get here. So this is composition, means the matrix multiplication we do. So there is a inverse. There is a inverse of it. Let's say I have a linear transformation T of this case. So generally, one thing you have to remember, that if you have a linear transformation, it's so the linear transformation should be of, it should be a linear operator, not a linear transformation. Linear transforms could be of any other to any other dimension. Okay, but inverse is generally, so not generally, the inverse exists for a linear operators, means here the whatever the output domain and input domain are going, output domain, output means range one, and the codomain, sorry, domain and range codomain have the same dimension, means range have the same dimension. Okay, and the inverse is going to be, as you know, this is, let's say I am saying the T inverse. So generally how we'll get the inverse, let's say I have given a linear operator T of x, which is x plus y and x minus y. So somebody is asked, find the T inverse. What is going to be T inverse in this case? So one way is very simple, find the matrix representation and then find the inverse of the matrix representation, and find the expression of it. Easily you can substitute. Okay, this is one way. This is the general way we'll follow to find the even inverse. Okay. Otherwise, yeah, I don't think there is any other quick method to do the fast way. So simple method is very simple, that find the matrix representation and then inverse of that matrix. For 2 cross 2, what is that? If you have A, B, C, D matrix, so what is the matrix, sorry, inverse of it? AD minus BC, and here is A is going to be in place of A is the same, B is going to be minus C, and it is minus B, and in place of D, so here is going to be D, and here is going to be, this is going to be A. So inverse is, by this way you can by this way you can easily find the inverse of it. But if it is a 3 cross 3, but if it is a 3 cross 3, let's say A, B, C, D, E, F, G, H, I. So to find the inverse, professor discussed the way it is. You can write like left side is like this, and do some operations. You have to convert this in identity. Once you start converting this in the identity, this will be converted in the inverse form. So doing the row operations, okay, whatever the operation R1, R2, only the row operation, only one operation will follow, okay, and to convert this in the identity, okay, and then slowly This will be, will try to do more and more operations, and this will be converted into identity. This side will be the same operation. Means you have to do, you are doing the operation, you have to follow the, you will use, you have to think that this is one row, this is another row, and this is the third row, and accordingly you have to do all of the row operation to all entries one by one. So this will be converted slowly after doing the operations. This will be in the identity, and this part is you will get the inverse one of this. So this matrix is the inverse of this matrix. Otherwise, you are following the minor cofactor from it and adjoint of the matrix. Using that, you are finding, you can find it. So one important thing is that the determinant of the matrix. If you are finding the inverse, the determinant of matrix is not equal to 0. This is what it is. So let's not waste time on this. Let's discuss the range and null. So these are some composition of the linear transformation and inverse. The next is null space and the basis of it, which is called null space. It is a null space dimension. It is called the nullity. Okay. And you have a range space, and dimension of the space is called rank. Rank. So if you have a linear transformation, okay, from let's say R3 to R2, okay, so there is some set of vectors, okay, there are some set of vector. You find the image, you will always get a 0 image. So if you collect those all vectors which have image as a 0, if you collect all those, that will form a space, subspace, and that is called your null space. Let's do one problem on it. So simply I have no this linear transformation p of x plus y, so sorry, x and y, which is of this case x plus y, x minus, or even x and y. Let's say I have this linear transformation, or x 2x plus 2y, and let's say y. I have this linear transformation. Let's find the null space of it. I have to collect all those vectors which have the 0 image. All of you just do it. What is going to be the null space here? Null space is nothing but so null space is not only find the basis of the null space. The question would be better that find the basis of the null space. Basis, you know, right? Basis is again, which is expand. So you need a basis element. Is this null space is 0? Is it? Anyone found it? Is it tough? Anyone has solved this problem? I'm not getting the concept of null space. Can tell. I will repeat it again to tell that what is a null space. Am I audible? Okay, anyone is solving that problem? Please just stop me. Please, again, I am saying, please stop me if I am going very fast. There is no mean of going very fast if you are not understanding. Okay. So if you are not understanding what is null space, I will slowly explain that what is a null space. Oh, okay, no issues. Let's discuss that. So there are two ways. So I hope null space is clear. But let's how we'll calculate the null space. So the first way is that convert or find the matrix representation. Okay, and then find the null space of matrix. What is the null space of matrix? So that is also I will tell you. Okay, and or a very simple, if you have
Sir,
expression is
Ax equal
given.
to 0.
Sorry,
Ax equal to 0.
ax, yeah, ax is equal to
Or
0.
last ones.
Sorry,
Matrix
sorry.
Ax, matrix A, x equal to
uh,
0.
Matrix A is equal to 0. You have to solve the system of linear equation, this one.
Yes,
Once
sir.
you find the matrix representation, solve the system of linear equation,
Yes, sir.
this one, and whatever the solution, that is your null space.
Yes, sir.
Or simply, if you going through with this one, in place of going this, very simple, as the definition of null space, no, it says that collect those vector which have the image 0. So let's assume that vector is even itself this one. If you have a problem, you can change to t of v is equal to 0, means here let's say v is our v1 and v2, and then v1 and v2, t of v1 and v2 is equal to v1 plus v2, 2v1 plus 2v2, and 2v and v2 equal to 0, because it says that collects those vector which have image 0. So let's proceed with that. This is what it is equal to 0. So you get v1 plus v2 is equal to 0, 2v1 plus 2v2 is equal to 0, and this last one will give v2 is equal to 0. So you got no system of linear equation. So if you proceed to this, if you find a matrix representation of it, it is going to be, now you can quickly do that. This is 1 2. Okay. This is going to be 1 2 0, and this is going to be 1 2 1. Now if you write, this is the matrix representation. If you solve the system of linear equation and equal to 0, you end up with the same, means x plus y is equal to 0, 2x plus 2y is equal to 0, and just y, yeah, z is equal to 0. Sorry, here it is not y, just y, no. Okay, this is y is equal to 0. See, this is the same, right? Only the in place of x y you are writing v1 v2. So same thing is there. Even if you are proceeding with this, in place of, the best thing is just you get to 0 and compare is that you will get this system of linear equation. Now this is v2 is equal to 0. Here v2 is equal to 0. If you substitute any one of them equation, it will give v1 is equal to also 0. That means the possible solution of this system is only the 0 0. That means null space is the only 0 space. So the only 0 space here. No other vector is there which have the 0 image. Okay. So simple. Either you can go with the matrix case or you can go with the directly. So this is actually skipping your some steps. So this is a null space. So sometimes you get non-zero null space, means here you will get the other element also in the null space. In that case, generally we need to find the basis of it. For example, let's say I have this linear transformation T of xy is equal to x plus y and 2x, or even x minus y, 2x minus 2y. Suppose this is the linear transformation we have. So what is the null space of it? So to find the null space, again, let's do with the same method, equated to 0. It means x minus y is equal to 0, 2x minus 2y is equal to 0. Both will combinedly give x minus y is equal to 0. That means x is equal to y. So what is the solution here now? This tells you the system has infinitely many solutions. So system and infinitely many solution means you can assume y is equal to 1. So x is equal to also 1. So this will give a vector 1, 1. Okay. So whatever the vector you got, this vector is actually, you can say, a basis element of the null space. So you got, so null space is now here going to be, null space is nothing but your is xy, where x is equal to y. This is your null space, right? Because this is what it is, x is equal to y. This is your null space. And the basis is going to be, you can take the as this vector whatever you got the solution. This is your basis of the null space. So whatever the solution, once you started solving it, you will end up with, for infinitely many solution you did already many times. You substitute for, you will think that okay, y has one, and whatever the possible solution you are getting, you will collect one vector separately another vector. So you will collect all vectors in this way and just say that this is a basis of null space. Okay. So or in different one you want to write, null space is nothing but your, in the case of somebody says okay, write in the basis form, so null space is nothing but your c time or x time 1 1, right? This is what it is, x belongs to R. In the span form, this is written in span form. So there are so many ways to represent a null space. So this is your null space generally in xy form, and this is your basis. Is this clear? No?
Yes, sir. Yes, sir. Clear.
Yes, sir.
Clear, sir. Clear, sir.
So let's move to the next is the range space. So range space is nothing but your collection of images. Like I'm writing T of xy is equal to just this linear transformation, x and 0. So see, this is an element of R2, okay, and image is not actually whole space of R2. It is a sub. It is, if you collect all images, it will be, subset of R2. Let's say I am collecting all image of T is going to be a subset of R2, right? But this is collecting only one part, and rest other, these this is not a image of 0 1. 0 1 is not image of, it is not an image. You will not get any vector which have the image have this one. So range space is actually collection of images. Okay, so range space or range space is nothing but, you can say that this is range space is nothing but, it's going to be T of just collection of vectors. If you just collect all vectors, images, just collect images, all images. So this will be a space. If it is a space, then it have a basis, and that is basis, and the number of element in the basis called dimension of the dimension of this space called rank. Like here, let's see, this is the linear transformation I have. So anyone can tell what is a basis of this range space, or what is the rank of this linear transformation? What is the rank of T?
1.
Anyone?
Sir, basis I think 1 comma 0 and rank
Rank 1.
Rank 1, simply. Number of element in the basis is rank. Yes. So here is basis is simply, because any vector or image could be, you can write 1 of 0, no? So this is behaving like your basis element. So you can say your basis element is, or basis is 1, 0. And only one element in the basis, so you can say the rank of T is 2. This is one way method to find it. Otherwise, you can find the matrix representation of it. Very simple. Find the matrix representation. So T of image of, so simply matrix representation, if you do it here, so T of image of canonical basis is going to be 1, 0. This is the first one. The second one, T of 0, 1 is going to be 0 and 0. So matrix representation of this T is nothing but 1, 0 and 0, 0. So now you just find the rank of this matrix. What is the rank of this matrix? Means convert that to canonical, some sorry, not canonical, to simplified in upper triangular form, and number of non-zero row, which is already it is in upper triangular form. Right? So number of non-zero rows will give the rank of it, rank of the matrix. So here is already very much clear that rank of the matrix is 1. So by that way you can say the rank of T is 1. Okay. So it is not so tough. Okay. So there is a now term that 4 fundamental space is there. And the first one is range, sorry, row space, column space, null space, and left null space. There are 4 spaces there: row space, column space, null space, and left null space. Okay. So before to start that, there is a rank thing is there. So rank is nothing but, if you find the row space of it, the dimension of it is called rank. Let me tell you that what is exactly. If you have a matrix, okay. So suppose this is a matrix where these are the rows we have. So a span of these rows is called a span of these rows is called the row space. So finding the row space is not enough. So it asks the find the basis of the row space. And the question would be asked basis of row space. So what is going to be that? So even sometimes question would be asked find simplified basis of row space. So let's do one problem and it will be very clear to you by the solving example. Let's say I have this one 1 1 1 1 0 1 0 1 1. Let's say I have this matrix. I will find the each spaces here now. What is going to the row space here, column space, null space, and left null space. These 4 fundamental spaces are there. So before to start, let's say I have a linear transformation. I will connect with the linear transformation also. Let's say I have a linear transformation from R3 to R3, and matrix representation of T is this A, this matrix A. So what is the expression here? So easily the expression is going to be x plus y plus z, x plus z, y plus z. Easily we can get right by multiplying this. So this is a linear transformation. Fine, totally fine. Okay. So this is your linear transformation, and this is the matrix representation of it. First I wrote the matrix and then I find the linear transformation. Okay. Let's find the row spaces, column spaces of this matrix. What is going to be? So to find it, the row space. So what is going to be here? You can just, even if you are writing like this, a span of these vectors, take the rows as column wise, 1 1 1, span of 1 1 1, 1 0 1, this one,
Yeah, it is
and
1 1 0.
0
First
1
two.
1. First two terms. Okay. So if you're writing, yeah, if you're writing row space as this one, this is fine. Row spaces, this is row spaces, fine. But I asked the basis of it, not only basis, simplified basis. So how will find the simplified basis? So what you have to do some row operations here. So let's, I'm doing the R2 minus R1. I'm trying to make it 0 here. So this is 1 1 1, and this is 0, and this is minus 1, and this is 0. And this is the operation I performed there. So I got this one. And let's do one more operation, that what I am doing in R3, I am in R2. In R3, I am adding R2. So this will be 1 1 1, 0, minus 1 0, and 0 0 1. Yes, this is what I will get. So now whatever this now, this is, in upper triangular form, kind of. So from here you can say that the basis is now, take this row, and this row. So simplified basis is even let's do one more step. More simplified basis is needed. So even what is that? You can say that you can add now in R1, you can draw R2. So this will be 1 0 1, and 0 0 minus 1 0, and 0 0 1. And also one more step I can do there. I can subtract from R1 R3. So this will be a 0 0 0 0 minus 1 0 0 0.
Sir,
So kind
R1
of,
plus R2, R1 plus R2, you are putting in R1, na?
in R1 I'm doing.
Okay.
In R1 means here the whatever the first one is actually on applying that.
Yeah.
So by this way, slowly we'll get the identity. Even we are getting the identity. So simplified basis is for the row space. You can say the 1 0 0, 0 1 0, and 0 0. We are getting. So this is the way to find the simplified basis, or the row space is this one, and the simplified basis of this is. And by this way, if somebody is asked what is the rank of this matrix, so I am getting the 3 element in the basis in the row of the row space, or the rank of matrix is also after getting the upper triangular form. From here you can tell, or the number of elements. So here are 3 rows are non-zero, so rank of the matrix is 3. Or even from the number of basis element in the row, basis element is also give the rank of the matrix. So rank of this matrix is 3. Even the rank of this linear transformation is also 3, because by this way, whatever you calculated for this T, this A matrix, is going to be same for T also. Because whatever we are doing on this, it is anyhow backend is happening for T. In backend, it is you are doing on T. So one way is method to find the rank of linear transformation is find the matrix of that, and then find the row space, and then rank. By that way you can. So this is the row space and the rank of linear transformation. This is the relation you can say, and these two things we have seen in a combined form. Column space is, let's do the column space of a matrix. So generally the column space is, I'm taking the same.
So null space will be 0 0 0, na?
Sorry?
So null space would be 0 0 0.
Here the null space is 0. Here the null space is going to be 0. We'll see there very quickly. I will just import from here directly to the terminal space. So let's first find the column space now. So column space will take the columns, and then the span of the column space is nothing but your 110 span of 101 and 111 span of it. But this is the column space, fine. But somebody says find the simplified basis. Okay, simplified basis of column space. So how we'll get that simplified basis? So simply I have this matrix A. We know only the row operations. So what we will do, we'll take the transpose of it. So this will be 111, okay, and 101 and 011. I took the transpose of it. Okay, now start solving this. Find the means in upper triangular form, or even if you do it again, if you do the now row operations, r1 minus r2, or even r2 minus r1 and r3 minus r1, you will find something. By that way, if you also, if you got one upper triangular form, and also not only upper triangular, start doing the reducing to the here whatever the non-zero, also make it 0. Slowly if you do it, you will end up with the identity only. You can check it even. You end up with the identity. So here see, same vectors I just wrote as in the, so whatever the means same vectors I just wrote in, so in a different method, in different way, I just wrote, I took these vectors and wrote in the column wise, or whatever I'm doing, transpose both are the same. Like writing these vectors as a column wise, that is what I did, right? Or even if you're writing the transpose is same. So here whatever the simplified one you got, right, this one. So take these vectors. This is going to be the basis of column space. Simplified basis of column is, take this as these vectors. Now you will not take the row. Many people have the confusion. They will start taking the column of it. No, you don't take, because you are doing operations on transpose one. So you have to take the rows. So simplified basis of the rows is just take the rows here. So this is also 100, 010, 001. Okay, it's this is very simple matrix. That's why you are getting the same. Otherwise, sometimes, not only many times, it generally differ from column basis, simplified basis of column, and simplified basis of row. Okay. Next is the null space. So to find the null space, take the matrix. It's the same matrix here. A 110, 110, and 010, and 111. And now solve this system of linear equation. So to solve n equative to 0. And now what is that? You have already done, or in different method change to, this is an simplified way, which is, if you do it, we will get, you do the row operation, so many row operation, and slowly change to very simplified form. And if you find very simplified form, this will get identity. That is what it is simply. Because we have done, right, many times on A, we did here, finally we got here the identity. So here is also identity will get now equal to, now back to the system of linear equation. From here, x is equal to 0, y is equal to 0, or z is equal to 0. Or even if you are directly not doing this, or you are solving from here, so this is x plus y is equal to 0, x plus z is equal to 0, y plus z is equal to 0. You have this system of linear equation, solve that. That is your null space. So here the null space for this matrix is 0 space. Okay, this is your null space.
Excuse me, sir.
Yes.
Sir, in the above example, why we have like transpose the matrix and then do the operations? Why can't we directly don't do the like operation on the matrix.
Column. So operations are what kind of operation you will do on columns or row?
So without transposing like on column.
Without transposing or doing the column operations or row operations.
Yeah, yeah.
So if you are not transposing, so do the only column operations. I mean to say fix with the only operations. Like if you are doing only column operation, if you are not transposing, okay, if you are not transposing here, so perform only the column operations. Don't do in that row operation. Don't mix with. If you are doing only column operation, do that. If you are doing only row operations, only do row operations. Okay. So I in the lecture we taught only row operations. If we taught column operation, then it is fine. But we learn only the row operation. That's why in place of doing row column operation, I transpose it and then start doing. So in back end, whatever you are doing here row operation, in back end you are only doing the column operation on the A. That is what it's happening, right? In the back end, here on transpose you are doing the row operation. What is happening in the back end? On A you are doing column operations. That's all. So that's why I did transpose, because we learn only the row operations. Otherwise, if you are very much satisfied or easy, you are doing easily for column operations, you practice a lot for that. So don't do transpose, do only on the same matrix column operation. It will not impact your solution. Okay. But my suggestions generally, we easier, the row operations generally find easier. Will get because it's properly visible, no? And columns you cannot see properly. So maybe, is it clear?
Yeah, sir, it is clear.
Okay.
Sir,
Yes.
can you do for me one matrix for complex, for fundamental spaces for A with
Mm-hmm.
complex number?
So with the complex number is okay.
Can
Okay.
I tell you the matrix?
Okay.
2 into 2, 2 into 2. That is column A equal to column wise 1 plus I, 1 plus I, 1. Yeah, and second column is 2, 1 minus I. We
Okay.
have to find 4 fundamental spaces of A. That is A equal to.
So okay, four fundamental spaces of A.
Yeah,
This is the matrix
yeah,
we have.
yes, yes, sir.
So here, okay. So if the question is find the simplified, so here find the row space. So row space is generally will write a span of.
Question is find the basis for the 4 fundamental spaces.
So basis is basis for four fundamental space.
Yes, sir.
So basis of four fundamental spaces. So first check that is this matrix is so even if you do, let's find the row basis of row space. So row space is generally what is that here? Row space is nothing but your uh, row space is your uh, span of 1 plus I, or even no, this is 1 plus I2 and 1 minus I. But one thing is, if you observe it, so this is the row space, fine. This is the row space. But let's do some operation here. So I am doing here operations. Um,
Sir,
Here is
I am
one thing new. If you multiply row 2,
Yes, sir. This is
with
C2 equal to twice C1.
so that is what is. If you multiply 1 plus I to row 2, this will be 1 plus I. This is 2 and this is 1 plus I and exactly 2.
Yeah.
Right, this, and finally what you can do, you can from row 2 you can subtract row 1, so you'll get here 1 plus I 2 0 and 0, right? Very carefully you have to proceed. So by that way you can say that now the basis is going to be For the row space is this is one dimensional and 1 plus I and 2 for the row space. Is it clear? This is how you can proceed. No? And now let's find the column space. So column space is nothing but your span of the columns, which is 1 plus I 1 and the 2 1 minus I. Again, so the column, but it is asked for the basis of it. So I usually do the transpose. So let's do the transpose of it. Here we'll do only the transpose. Here we'll not do the conjugate transpose. Okay, we'll only do the transpose because we are performing only the row operations. So just do the transpose here. Otherwise,
Sir, not
if you are
conjugate.
now from here, it sorry,
Not conjugate.
not will not do the conjugation. No, we don't want that. We are doing the transpose for our simplicity. Okay,
Okay.
we are not finding here the left null space. We are doing this operations, or I am doing the transpose for our simplicity, for our to do for our to do easier, like to ourselves, so that easily can do operations. We are not
Sir,
doing anything. Yeah,
if we multiply column 1 by 1 minus I, then we could easily justify that the second column is multiple
yeah,
of
that
this.
is, yeah, that is what exactly. So this is for my purpose. This is totally fine. Otherwise, if you are able to observe that this is the same as if you just multiply the first column, or mean to say the column 1 is just multiplying with the 1 minus I and 1. The column, this is column 2, right? The column 2 is nothing but 1 minus I. So if you are writing like this even, so from that way you can say the basis for column spaces. If you're in the proper word, how you can write if you are writing the subjective, so you can directly write even if you're not doing the transpose and other operation you don't want to do it. So here you can write like this: observe that column 1, which is 1 plus I and 1, and column 2 and 1 minus I. Observe column 1 and column 2. Observe from column 1 and column 2. Column 1 is equal to, or 1 minus I and 1. Column 1 is equal to column 2. This is the observation I got. And so basis is going to be, you will just take any column. You will just take any column. That is your basis. That is your basis. Only just need to observe. Otherwise you want to do means this is what I generally do, but observation is itself tell you. So however, it's depend on you. It's make us clear that you are observe that this is what it is, and so the basis is this one. You want to reason, no? Means if you are writing in any subjective question, reason we want. If you see in any proof, if you do BSc mathematics, only only the
Similarly,
reason we
column.
want. What is that? Sorry.
Sir, similarly, basis, for row basis, answer is 1 plus I. 1
1 and
1 minus I.
1 and 1 minus I. That is also, it is also a simplified basis. Or if you multiply with this by 1 minus I and 1, it will give the same, right? So either this is answer or this is your writing. This is both are same. If you're doing the conjugate of it, it's not impact, if you're not, it is a conjugate. What is that? You are
So
just
my
multiplying.
confusion is that which one I will take? That is the basis, simplified basis we have to take then.
So simplified basis is this is also now what is a simplified means what? You cannot do the further simplification in that. This is also a kind of simplified, no? If you what now what you want to do, you want to multiply here 1 with 1 minus y and 1. So if you multiply here, this will be so sorry. If you multiply with no sorry, if you multiply with 1 minus I, sorry, if you multiply with only single, sorry, one scalar 1 minus I. If you multiply, this will be of 1.
So 1 minus I in
So
and 1.
what you are saying? You are saying 1 and 1 minus I, right? You are saying this is the
Yeah,
simplified basis.
yeah.
This is a simplified basis. So this you can know this is nothing but this vector is exactly that one. You can think that you can just divide by 1 plus I. If you divide this one, this you will get this is what it is. This will become 1, and this will be the second. This is 2 upon 1 plus I, and 2 upon 1 plus I is nothing but if you do the rationalization, this is 2 into 1 minus I upon 1
1 plus 1, that
1
is
square.
1
This is what it is going to be, and this is finally means you will get 1 minus I,
minus I. Yes.
which is 1 minus I. So here either this is your writing or this is what you are writing. Both are the simplified only. So only one is what is a simplified means you not do the further simplification, but this is also a basis and also it is a simplified bit. What is the meaning of multiplying this or dividing by 1 plus I?
So sir, my question is, if I write the basis row space is 1 plus I2, that will also be correct.
That is also correct. Totally correct. No marks would be deducted
Okay,
here.
okay, sir.
Okay. So these are some. So if you're writing like this, you want to observe that or that this is happening. This is very much clear to. Okay, you are observing. This is what it is. Okay,
So
so this
sir,
is the
for
null
column
space.
space,
Last thing.
we have only
Mhm.
to find for complex number only transpose, not conjugate transpose.
Oh, so for this is for our purpose. So yeah, it is here is you are doing for the left null space. You have to do conjugate transpose. Okay, for the left
Okay.
null space. So the question is find the left null space now. So here is a column space you are doing to find the column space for yourself to only the row operations. That's why I am doing the transpose and performing the operations. This is what it is. Okay. But many people have doubt. Okay, what is in the null space we are doing the only transpose? No, in the left null space definition said that find the A Hermitian and then find the null space of it. That is your left null space. You see the definition here. The left null space is finding the Hermitian and then null space. And
Okay, sir. Okay.
okay, and for the if your matrix is real, then find the just transpose of it and
Just
then
transpose. Yes. That
null
will be
space.
fine. But I got confused in complex number.
So here is only so be clear with that we are doing this transpose for our simplicities or for make our to do the easier calculation. Right? If you are very much clear with the column operations, don't do this. It's not needed.
Yes, sir.
Exactly not needed.
Yes, sir.
Okay. So let's move ahead. Our topics now left for fundamental spaces system, inverse system, matrix representation, range, null, basis. Let's move to our eigenvalues, eigenvector, diagonalizability, and these are very tough, fast topic. There is no it will not take much time because from many times we are doing the eigenvalues. So I will just tell you, will do one problem on it, and everything will be clear. So eigenvalues and eigenvectors. So it is one. I will just tell you that if you have a matrix, okay, if you have a linear transformation even, if you have a linear transformation, not only linear, we only stick with the operators. Okay? Operators is that the domain codomain have the with the same dimension. That is your operators. So let's say I have a linear operator. So it is one property, no? Property is that not property. In this vector space, there are some vectors. There are some vectors. If you find the image, no? If you find the image, it will give the image. Okay. But these vectors, no, these vectors are not only the vectors. It is very specific vector. And what is specific means it will just lambda time v image you will get. You will not any other v prime. I mean to say, let's say I have this linear transformation t of x y is equal to x plus y and x minus y. I have this one. Okay. So if you find the image of 1 0, this will be 1 1. Okay. This will be 1 1. But this linear transformation is from R2 to R2. Okay. So I am finding image of 1 0, I am getting 1 1. But within this R2, there are some vector. If you find the image of it, no, it will be the same lambda time v. And these vectors are called eigenvectors. These very specific vectors called eigenvectors. Okay. So like here, you are getting t of this v is not exactly this v. This is a different. But for these vectors, which is called eigenvector, this property have. Means it is just scaled up. It will not change the direction. Here you have this vector which have some direction, and once you found the image, the direction is changed now. But for the eigenvectors, you have the whatever the image you are taking, whatever the vector you have, you are take the image. The direction is same. Direction is not changing. Only just scale up or scale down. It's happening, not changing the direction. This is the property of eigenvector. And we know, right, there is a 1-1 correspondence between the matrix and linear transformation. So here is, if you have a matrix representation A of this T, then this will happen. T of V is equal to lambda time V. The same thing, because finding the image in place of is that just multiplying the vector with matrix, in the matrix case. Right, we did already. I think we are able to catch it. Many times I am discussing it. So finding the image means just doing the matrix multiplication of that V. So which is nothing but A minus, you want to find this V. So the process is, if this is there, so one algorithm is generated to find this vector, what is going to be there. So to find that, we generally do the matrix of it and solve by saying to be this. Means find that this matrix first, or let's say assume you have, what is that, you have matrix is given. Let's say I'm now giving example the process to find that 1 1 1 0. And this matrix I will do lambda times 1 0 0 1. I will find this matrix. Okay, this is going to be 1 minus lambda 1 1 and 1 minus lambda, sorry, minus lambda. This is the matrix you will get. Okay, from this matrix we'll get this matrix. If our matrix is 1 1 0 1, sorry, 1 1 1 0, if I have this matrix A, we'll follow this step, and by this way I got this one, and find the determinant of it. This is going to be 1 minus lambda and minus lambda, and this is minus 1 equal to 0. So this will be lambda square minus lambda minus 1 is equal to 0. And now you will find the root of this. So this you have a polynomial, you have to find the root of it. And once you found the root, so let's find the root here. So see, this is not easy. I think I made a mistake. 1 minus lambda 1 1 minus lambda, it is fine. So this is minus lambda time minus lambda
This
minus
will be
4.
complex number, na?
Sorry.
Lambda will be complex.
So here it's looking like a complex
Value.
we'll get. So let's do
Yeah,
that.
then
So
it will be
lambda is
complex.
into minus b plus minus b square minus 4ac. We'll follow this root square method. 0.2a. So this is going to be 1 plus minus b square is 1 minus 4ac is all 1. 0.2a. This is 2. So this is 1 plus minus I root 3 upon 2. This is what we'll get here. Or in different way, the first lambda 1 is going to be 1 plus I root 3 by 2, and lambda 2 is going to be 1 minus I root 3 by 2. These are the roots you got. So these roots are called eigenvalues. Okay. These roots are called eigenvalues. Now you will substitute one by one in that matrix. Our matrix is A, which is 1 1 0 1 1 1 0, and now you will substitute here and solve the linear equation. 1, so we'll take one first lambda, which is 1 plus I root 3 by 2, and the identity 1 0 0 1. You'll get a matrix this. Solve the system of linear equation equal to 0 0, or this is here, this is the next step here, and it's equal to 0 0. So here finally we'll get here 1 minus, or here it is going to be 1 2, this is 2 minus 1 minus. This is the matrix I think you will get here finally if you solve. This is the matrix you'll get. This is right. I think 1 minus 1 plus I root 3 by 2. So this is 2 minus I 2 minus 1 minus I root 3. This is 1 minus, yeah, 1 minus I root 3. So this is what the matrix will get here. So let's solve the system of linear equation. If you solve the system of linear equation, here it will be, no? So if you observe, this is again, a row rank 1 matrix. Here is just I time is there, it's happening. If you do it, this is what it is happening here. This minus I time it's happening here. So observe, you will get only this. Means here, if you do some, what is here? If you multiply row 2 with some number, which is even, no, you want to make it, or if you divide row 1, or if you multiply row 2, this row 2 with I minus, sorry, 1 minus I root 3 by 2. If you multiply this one here in row 2, you will exactly get this row. You just need to observe. If you multiply row 2 by this one, you will get, this is row 1. This is your row 1. Exactly this one. So this is just observation is there. So mean to say, if you solve the system of linear equation, you can write 1 minus I root 3 by 2 x plus y is equal to 0. This is what you will get. The second row you can easily make it 0. And from here y is equal to, you will get here minus 1 minus I root 3 by 2x. So from here you can get the eigenvector as, if you substitute x is equal to 1, you will get 1, and the y is equal to minus 1 minus I root 3 by 2. This is one eigen complex vector u. So very bad thing, we got all a complex number, but many people have hesitated that, okay, if we got this complex entries, how we'll do this? So that's why I am doing. Okay. So for the eigenvalue lambda 1, which is 1 plus I root 3 by 2, I got the corresponding eigenvector is this one. Similarly for lambda 2 also, we'll same follow the procedure, which is 1 minus I root 3 by 2, and also we'll get a eigenvector. So by this way, you will calculate the eigenvalues, eigenvector. Very bad thing, we choose as a really wrong matrix and slowly end up with the very complex eigenvalues and eigenvector. But doesn't matter. It doesn't matter. It's good we are doing on complex. So see, the matrix is real, but eigenvalues, eigenvectors are all complex. And this is how we'll find the eigenvalues and eigenvectors. Okay. So suppose, is this clear? Is this what I'm doing? Is it
Yes, sir. Clear, clear. Yes, sir.
So this is what the thing is, that we have a matrix, and by this way we'll follow the eigenvalues, eigenvectors. So there is one thing is that multiplicity, which is called algebraic multiplicity and geometric multiplicity. So algebraic multiplicity is what? Sometimes sometimes the characteristic polynomial, let's back to over here, this characteristic polynomial. It is, suppose by chance you have a matrix of order 3 cross 3, 3 cross 3, by chance I am saying even 2 cross 2, but the characteristic polynomial you got like this, lambda square minus 1. For the time being, I don't know what is the matrix, but I follow the procedure A and I got this characteristic polynomial, A minus lambda you do all. So see here, the lambda value is, you got 1 and 1 twicely. You got the eigenvalues 1 and 1 twicely. So that means you have one eigenvalue, only one eigenvalue. You have only one eigenvalue, which is 1, which is here 1. But it is twicely is there, no? So it is called algebraic multiplicity. It is twicely, so it is called algebraic multiplicity is 2. Okay. So if eigenvalues are repetitive, then how many times it's repeating, that is your algebraic multiplicity. Clear? Now, suppose you are proceeding with, okay, now you have this matrix A, which have this this one, and you got eigenvalue as 1. So 1 minus the matrix A, and then 1, and then identity, and you solve a system of linear equation xy is equal to 0. You solve this. You solve this. And you have started solving. You end up with the system of linear equation. Okay, and by that way you got only one. Okay, see, only one means you have only one eigenvalue. A minus lambda. You have only one eigenvalue. Okay, so for the
Excuse me,
first one, so yes.
sir, if we have the one root that is one time repeating and the second root is two time repeating, then what will be the algebraic multiplicity?
The one root is one time repeating,
Or we can say it is two time repeating and the second root is three time repeating. So what will be the algebraic multiplicity?
so what is in that case you are saying? Your means you are saying the eigenvalues are 1 1 and let's say another 2 2 2. That is what it is you are saying.
Yeah.
So that means your matrix of order will be surely 5 plus 5. Okay, your matrix of order 5 plus 5. That's why here you are that many roots you will get, 1 1 and 2 2 2. So here your eigenvalues, if you say your eigenvalues are only 1 and 2, you have only eigenvalues 1 and 2, but algebraic multiplicity of 1 is
We have to write separately for separate eigenvalue.
for this one, for here the algebraic multiplicity is 3. Separately you have to write for this lambda eigenvalue lambda 1, for this lambda eigenvalue lambda 1, for this lambda 1 you got, for this one is algebraic multiplicity 2, for this lambda 2 you have 2.
Yes, I got
Okay.
it.
So this is the algebraic multiplicity. Now what I mean to say, So if you start doing to find the eigenvalues, so you have only one eigenvalue, right? You have only one eigenvalue, so you will do a minus lambda I. But the chance is that once you start finding that, and the system of linear reaches to system of linear equation, as we have reaches there here, this one, and solve and got that okay one eigen. So he got. So the chance is that suppose because we have this is a repetitive, so the condition should be it should be two, means it should be two independent eigenvectors you should to get. But your bad luck is that you only got one. So for the one eigenvalue, you are only getting one eigenvector. For you have only one eigenvector which is repetitive, but you are not getting two independent eigenvector. You are getting only one. So in eigenvector, sorry, the eigen number of eigenvector, which is called geometric multiplicity, here is one. But by chance, if you are getting two different, two independent eigenvector, in that case, the geometric multiplicity is called two. Okay. It's called very simple. If you do the example of identity matrix, okay, one. Suppose I have a matrix, not identity. I have this matrix, which is it's exactly identity matrix. But if you find the eigenvalue of it, here the eigenvalue of this matrix is very much clear. If you do a minus lambda I, it will give it will have a lambda a characteristic is this one. If you find the determinant of it, this is going to be this is, and eigenvalues you will get 1 1. Okay, so if you do a minus lambda I, which is a minus 1 I,
1 minus 1, sir.
Sorry,
it is 1 or minus 1.
it is
Lambda
going to be
square,
1.
lambda square is equals to 1, lambda is equals to plus minus 1.
Okay, I think then okay, I think then I'm making mistake. This is going to be 1 minute. So let's do that. This is going to be 1 minus lambda. Okay, this is not this is going to be this one. Sorry. In this case, this is going to be 1 1, right?
Yeah, correct.
Yes, sir. Yes, sir.
This is 1 1. So see that how now I eigenvalue. So eigenvalue as 1. So a minus lambda I, which is 1 minus I, and now this is equal to 0 0. Let's solve this. So this is going to be 0 0 0 0 matrix, right? A minus 1 I, if you do this, will get you only 0 0 matrix. And now you have see it have means 0x plus 0y is equal to 0, and 0x plus 0y is equal to 0. If you convert in the
Unlimited
system of
solutions, sir.
so it means you are not able to fix what is the value of x and y. Means independent values are have x and y. So you can give independent value to x. Let's say I'm giving 1 and y as a 0. So you got a vector 1 0. Similarly, I can give any. I am giving as an independent value x. So now I am giving another x is equal to 0, y is equal to 1. By that way, I can generate another vector. So these two are exactly different, means independent, these two. Somebody says, why you are not giving x is equal to 2? So I can give x is equal to 2 and y is equal to 1. Let's give this. So you will get a vector 2 1. This is 2 1, right? This is one vector. But I also give any value to, so let's say I am giving x is equal to minus 1 and y is equal to 0. So this is minus 1 and 0. This is also eigen. So you will say, okay, I am getting 4 eigenvectors here, but not 4 here. If you see, if you check, these two are independent. Okay. If you take any these two off, those are going to be independent. If you combinely say these three, if you take combinedly, these are not independent, these are dependent. Okay. So I want only 2. So that means I mean to say here, so that's why generally we take here x as 1 and y as 0 to looks simple and easier, means a simplified. No, we want generally simplified. So this is one simplified. Otherwise, what is if we're writing 2 here, 2 is nothing but 2 cross 1. right? This is 2 cross 1, one multiple of it. So this is a multiple of it, right? So that's why we don't generally took 2 in place of. We take generally 1, simplified one, and y as 0. Very simple. 2 distinct number I want. So 1 and 0 generally we take, and that's more simple. So by that way, we
Sir,
will not take these two. It's depend on you. You can take, but
sir,
uh,
sir, when we take 1, x is equal to 1 and y is equal to 1.
so if you're taking 1, yes, okay, let's take it. Okay, I'm taking x is equal to 1 and y is equal to 1. So I get one vector 1. Okay. So you
Yes,
got 1, fine. But here is x, y, and totally dependent. Can you tell any other which is independent of these two also? Means sorry. So here I am getting x is equal to 1 and y is equal to 1. I am getting one vector 1. Okay. So you gave one. So another value can you give which is totally different with this? Totally different with this.
1 1 0, sir.
X is equal to 1 and y is equal to 0. So by that way you got a vector 1 0.
But sir,
So
if we
this
take
one
0 comma 1, then the both 3 vectors will be linearly independent, na?
0 comma 1.
Yeah.
Now
x0 y0.
you are saying you are taking x is equal to 0, y is equal to 1, and you got 0 1. So you are saying these three are independent. These three are not independent, right?
Any of two are linearly
Any
independent.
of two is independent. That is what. Any of two is independent. These three are not independent. So that is why it is to more like this. If you take these two, this is more simpler in comparison of if you are taking these two, right? So these, if you are taking these two, this is much simpler in comparison of this one, or if you are taking this one and this one. If you are taking these two, the best simple one is taking these two only. This two. So that's why means here it is very much obvious. I can give two independent values differently to get generated. From here it is very much clear that x and y is totally means free, exactly free. But we are generating vectors using this, so which will give two independent eigenvector, and very simple independent eigenvector is generally this one. That's why that is a standard we generally follow. Let's give x is equal to 1 and y is equal to 0, and next is y is equal to x is equal to 0, y is equal to 1. This is general standard form generally we follow too. Very simple, very easy. Okay. So see, the thing is that I was started from here. I have a matrix, this identity matrix, and followed that. Okay, see, for only one eigenvalue, which you have only one as one eigenvalue, you are getting two independent eigenvector. So here, what you can say, one the eigenvalue one have algebraic multiplicity is
2,
2.
2, sir.
Geometric multiplicity is you are getting two, right? Two independent eigenvector with respect to the same eigenvalue. So here geometric multiplicity is 2 also, right? Because here
And
is once you
there is a very important relation also. GM is less than equal to AM.
that is the GM is always less than or equal to AM. This is what generally it have. GM is always less than or equal to geometric multiplicity is always less than or equal to algebraic multiplicity. So this is the
Sir,
generated one. But sometime is that sometime is possibly you don't get two different, two independent. Sometime you may get only one. So these are the relations. Now recall from many times you are spending on. Just try to do some problem. You will get more idea on the AMGM.
sir,
Mm-hmm.
sir, I am leaving. Sorry, sir, I have emergency work from
Yeah,
home.
almost done also. Almost done. Now nothing is there. Only diagonalizability. Yes.
Sorry, sir.
Yeah.
Okay.
So almost done. We have done. We are almost done the topics. Only the diagonalizabilities remain. Only this matrix
Sir,
form.
can you do that with the three variable example, like three variable, three equation, and then finding the vector?
Yeah, we can do that easily, but yeah, it will take time. So yeah, it will take time. And but what you want to understand it?
So I get confused in like choosing the vectors, how to take independent and dependent variables.
So in that case, I will exactly end up with the on the matrix. Let's say I have a 3 cross 3 matrix, and you follow the
So
eigenvalues
you can
step.
you can directly like take any three equations and then
Any three equations. So I so by that way you got this system of linear equation: x plus y is z is equal to 0 and y plus z is equal to 0, or even let's say yeah, z is equal to 2, even yeah,
and one
uh,
more equation we want.
or even y plus z is equal to 0. Let's say you got this one. Let's say you end up with only these two. No, it doesn't matter.
Okay, okay.
You end up with this one. If you end up with this one, so let's do that here. So this will give this one tells you y is equal to minus z, and here is y plus z is equal to 0, which is exactly 1. So this will give x is equal to 0, right? This is, if you substitute, this will give x is equal to 0 and y is equal to minus z. So by that way you have a system which is of this case. So y is we having like a independent, z is a dependent, which is 0 value. No, it means we got the x value 0. Y is dependent on z. So by this way, you want to find the eigenvector. So you can assume z is equal to 1. So this will give y is equal to minus 1, and x have already 0. So by that way, you end up with one vector, this one. But suppose the case is that this is happening, x plus y is and z. So
But sir,
suppose your next is
if we write so z equals to minus y, then y is dependent on z.
doesn't matter. Y is,
Other
you can z
sense,
is equal to minus y.
so
So you
in
can
other sense, we will
give y
get
is as 1, and by that way you can give sorry, I just made a mistake. No, here x is 0, y is minus 1, and z. This is the vector really. Here for this case, y is 1, so y is 1, z, y is 1, z is minus 1, and x is already got 0. So it doesn't matter, you can multiply. You are getting these two vectors are just a small modification. If you multiply with minus 1, you are getting this vector, right?
yeah, yeah, correct.
So however, it's totally depend on both answer are correct. Both answers are correct.
So we are getting only one solution of this, like basis 0,
Huh.
minus 1, 1.
Only this have only one solution. Suppose you end up with this kind of system of linear equation, this one. So this have two independent solution. This have two. So now this way you can say that x is equal to minus y minus z. And so you have y is equal to x is equal to minus y minus z. It means what? Two independent variable you have. So two independent variable you have. So in that case, you can give y as 0 and z as one value. So by that way you will get what? So by that way
X
you
is
will
equal
get,
to minus
this
1,
implies x is equal to minus 1.
minus 1.
So here is minus 1, 0, and 1. One vector you got. So you assume you have given the value as y is equal to 0 and z is equal to 1. In the next step, you can give y is equal to 1 and z is equal to 0. And by that way, you will get x is equal to minus 1 again. And now you will get here x is equal to minus 1, y is equal to 1, and z is equal to 0. Now if you check, these two vectors are not, these two vectors cannot
Linearly
contain as
independent.
some alpha time. These are independent, totally independent. and we want such type of vectors. So you have to
I
choose like that so that you will get two independent eigenvector, because you have two independent variable. Okay, here it meaning that if you have two independent variable, that means you will get two independent eigenvector. Here you are only getting one independent eigenvector, so you are end up with only one vector. So how many independent vectors you are getting, that many eigenvectors, independent eigenvectors you will get. Is it clear?
Yeah, sir.
Is it
Clear,
clear?
sir. Yeah, totally clear.
So this is the things we have. And now once we, let's back to our diagonalizability, that last remaining part, and the power matrix. So diagonalizability is, now once we got this, where is that? This one. Uh, uh, uh. Yeah, I was here for the identity matrix. So once we got the two independent eigenvector, which is we got here, no, V1 and V2. We got two independent eigenvector. So what we can write, our matrix A could be, we will use to form this. We'll use to form a matrix S, which the S matrix is nothing but your right as a column wise, V1, V2. This is going to be 1 0 and 0 1. This is the matrix X. So finally, what is that? This says that the matrix A could be written as a S and the D and the S inverse. Your D matrix is nothing but your eigenvalues, lambda 1 0 0 lambda 2, which is here 1 0 0 1, because eigenvalues are 1 1. So finally, it means that you can write your matrix A as the S, which is 1 0 0 1, and the D, which is exactly 1 0 0 1, and the inverse, you can, if you check, inverse is nothing but the also going to be 1 0 0 1 identity matrix. So the identity matrix could be written, means here I just solve for identity, means you're multiplying 3 times identity will get identity. So but I want to give you a just idea that this is what is happening, and this is called diagonalizability.
Too much identity, sir.
To make simplify, to discuss within the time
So
limit,
like
that's why
we
I
can
chose this.
also like also write a to the power k as d to the power k s minus 1.
So finally, a power k is going to be s d power k and s inverse. So mean to the finding the power matrix is writing on the d power k, where d power k is nothing but s, and the lambda power k is 0 lambda 1 power
Here
k
only
minus 1 power
identity.
lambda.
Any power we will get identity.
So that means here finally here identity is there, so it is anything, but it is the generalized. This is the meaning of finding the power. So here a matrix is diagonalizable when you are able to find the two independent, or when the AM is equal to GM for particular eigenvalue lambda I. Okay. For a particular lambda I, okay, for all I it's happening. For all I, how many eigenvalues you have, for all I it's true that AM is equal to GM, means that many eigenvectors you are getting. Means for each lambda I, you are getting one eigenvector. For lambda 2, you are getting one eigenvector. For lambda 3, you are getting one eigenvector. And by that way, you are able to form your, this is V1, this is V2, this is V3. So V1, V2, V3. You are able to form your S. If you are able to form your S, you are able to find the matrix S, then it is diagonalizable. If not, then it is not diagonalizable. And once you found, then everything is sorted, finding the power matrix are all. And this is all the theories We covered lots of topics within the only the circulant is remain. I purposely wrote this, but we will discuss in the last revision session, the third revision session, because there is also circular matrix. So will keep. I just wrote here, but I will discuss in the last one because we will mix with this and finally discuss the circular matrix.
Sir, when last session?
Today is Wednesday, Thursday, on Friday.
Friday
I
evening and
think
Saturday
Okay.
evening, I guess.
Friday and Saturday. The last one is as TA also. That is what the one missing part is always. It should be clearly mentioned which one is. I don't know why Lavanya is not mentioning which one is TA and which one is instructor session, but it should be mentioned. So I think on Friday or Saturday, it should be any of the. I generally it is on Friday only because today we have, tomorrow one Lavanya will take, and the next last one is probably I will take, and that is going to be the last revision session. There we'll discuss 11 and 12, and 11, 12 topics. Remember quadratics, adjacency matrix, circular matrix, and spectral theorems. These topics are there. Interesting topic. We have discussed a lot on 12, 11, 12. So these are the topics we
Sir,
have. Interesting
sir,
topics. I hope.
please,
Mhm.
sir, please update graded assignment and practice assignment solution of week 11 and 12.
Yes, yes. I already told. See, have messaged. So, yeah, already sent to Kavit. It's already sent to Obstein, and uh, it's already sent to Obstein. It will be updated. Okay.
Okay, sir.
Sir, or else you can update in G space.
G space. Okay. 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 Let me L2 give G space. Okay. I think I told her to give link. She maybe provide. Okay. Okay. That's all for the today. Thanks for joining. We'll see you on the
Thank you,
next.
sir.
Any
Thank you,
doubt?
sir.
Any doubt?
Thank you, sir.
Okay. Yeah.
No, sir.
Thanks.
Thank you, sir.